No idea where this is coming from. I'm just making it up. I don't know. Even though you are all away from me, I can hear some of you saying, read! I can hear some of you saying. Turn in your books to page 582, and let's look at lesson 11-3. We are continuing our march through the world of rational expressions. And again, a rational expression, we define some r of x such that is the ratio between two polynomials, p of x and q of x, right? We've looked at what make for the excluded values of a rational expression. Hopefully we are familiar with the idea that our denominator cannot be 0. So any zeros of the denominator, any zeros of the polynomial q of x are excluded from the domain of r of x. Basically, in other words, anything that would cause this to be 0 cannot be plugged in up here. I don't know why I'm drawing an arrow. Remember, domain is what you can plug in. So again, anything that would cause the denominator to be 0, you are not allowed to plug in. So we have to remove it or exclude it from our denominators. Now, today's lesson, we're going to have a lot of denominators. We will be looking at some excluded values, but also on something like example 1, well, particularly with monomials, but when we have all these different variables, we're not going to worry so much about excluded values. Yeah, I don't know. We'll see. So if what we're multiplying, we want to multiply some rational expressions. One of the big things you want to keep in mind about these rational expressions is they do act a lot like fractions. So let's think for a second, how do we typically multiply fractions? If I had something like 2/3, and I wanted to multiply that by, say, 4/5, what do? Well, we simply multiply across the top, multiply across the bottom, and that's that, right? 8/15 is the resulting expression. Occasionally, you might have something like 7/19 times 6/21 times 5/23. No idea where this is coming from. I'm just making it up. And we could multiply all the way across and get some very large number. What would that be? 210 divided by, 19 times 23 is the same thing as 437. 437 times 21 is going to be 800,740 plus another 437. Why am I doing this by hand? I could just get the calculator out. 9,177. But those are some numbers that we definitely don't want to have to simplify at this point. And it turns out we can simplify them, because what we could have done is at this stage right here, we could have said, oh, I actually see some common factors, right? I can see that, for example, 7 goes into 21 directly, and 3 goes into 6 directly. And so this actually just ends up being 10 over 437, which is equivalent to this fraction right here, but it's the simplified form, right? So some things that we're thinking about as we multiply these rational expressions is, again, you can multiply right across the top, right across the bottom, numerators by numerators, denominators by denominators, but you can also be canceling any common factors that you see. So let's take a look at that in practice, because it's especially obvious with our monomials, which is what example 1 is all about. So let's say we have 5ab cubed over 8c squared, and we want to multiply that by 16c cubed over 15a squared b. Now again, I've already shown you, we could just multiply all the way across the top 80 a b cubed c cubed over 120, a squared, b, c squared, and then do the simplification. Obviously, some zeros come out. An a cancels with an a squared, leaving an a. B cancels with b cubed, leaving b squared. C to the third over c squared leaves a c, and then even 8 over 12, 2/3. And so that gives us 2b squared c over 3a. So that will definitely work. If that makes sense to you, more power to you. Just do it that way. But my preference is to look at this and say, well, what can we just cancel right here before we multiply stuff out? Like, let's try to make stuff smaller. So 8, for example, clearly goes into 16 twice. 5 goes into 15 3 times. And then from there, mostly it's the same. A cancels with a squared, leaving an a to the first. C cubed and c squared cancel, leaving a c to the first. And again, it always leaves the variable wherever the larger exponent was. B cubed over b cancels to b squared. And so I can see left over a b squared, a 2, a c to the first. In my denominator, a 3, and an a to the first. And so I get 2b squared c over 3a. Definitely the same answer, right? Method doesn't change the answer. In this case, the order in which I do stuff, whether I multiply first or cancel first, since canceling is a multiplicative process anyway, the order doesn't really matter either, we get the same expression. Like I said earlier, we're not going to be super concerned about excluded values here because all of these were monomials. A cannot be 0, b cannot be 0, c cannot be 0. So that is worth thinking about, but it's not really the focus of today's lesson. Oh my goodness, the book also did the 2 different methods. Genuinely did not realize that, but there you go. That's also in the book. Take a moment and work out Check Your Progress 1A and 1B. Birds chirping outside. That's unusual. Well, it would be unusual to you if you knew what time it was. One quick note, jumping in as I'm finishing up Check Your Progress 1B, you may do multiple rounds of cancellation because you can see it gets a little confusing with all the different things I've crossed off at this point. So just watch out for that. I try to do this thing where I kind of highlight at the end. I still have a G there, still have an H, still have a 3, still have a G squared, still have a 16 in the denominator, still have a J squared. But certainly it can be hard to keep track of all that stuff. If we do, though, we should get, for Check Your Progress 1B, 3g to the third, because I have 1 here and 1, 2 there, h over 16j squared. And g, h, and j, none of them can be 0. Okay, so there it is. Those are your answers for Check Your Progress 1A and 1B. D to the third over 2 CF squared for Check Your Progress 1A. None of C, D, or F can be 0 because those are all present in our denominators. And on B, same thing, G, H, J, none of them can be 0, but the expression simplifies to 3g cubed h over 16j squared. So multiplying monomials, we've essentially done that before, or I should say multiplying rational expressions with monomials as numerators and denominators. We've essentially done this before with our power rules. What you are really going to be interested in, I presume, is whatever is going on for example 2, right? So we have x minus 5 over x times x squared over x squared minus 2x minus 15. Now, first of all, a digression, because I'm sure from the last lesson, several students are wondering, why on earth can't we do something like cancel these x's out and say that expression is negative 5, right? Well, there's several reasons we can't do it. First of all, it's just not true. So imagine we have x minus 5 over x, and we say let x equal, 10. If we do that, the expression would turn into 10 minus 5 over 10, right? Because x is supposed to be 10 everywhere. So that's 5 over 10, which is 1/2, which is not negative 5. So it just doesn't work. So you might think, oh, maybe there's some weird way that the expression is supposed to cancel out to 1/2 instead. But what if we say, well, no, let x equal 5 instead? No, let's not do 5, actually. Let's do negative 10. Then it would be negative 10 minus 5 over negative 10, or negative 15 over negative 10, which ends up being 3 over 2, or 1.5. So as we change x, the expression itself changes, and it doesn't change in a way that appears to be related at all to that negative 5. It simply does not work. Same thing with the second part of the expression, x squared over x squared minus 2x minus 15. Even though you are all away from me, I can hear some of you saying, read, I can hear some of you saying, let's just get rid of the x squared, right? Let's call this 1 over negative 2x minus 15. But again, let x equal anything. Let x equal 4, let's say. This would end up being 4 squared, which is 16, over 16 minus 32, minus 8 minus 15 equals 16 over negative 7, I believe is what it works out to. And if we plug 4 in up here, we get 1 over negative 8 minus 15, 1 over negative 23. Those are not the same fractions. And of course, if we changed x, it would change the value of the expression. So this is just not going to work the way that you want it to. We can't cancel out individual parts of a factor. And think about it with an actual number, right? Imagine you had something like 3 plus 4 over 3. You probably recognize easily enough, oh, well, obviously that's 7/3, right? Or 2.3 repeating if we typed it into a calculator. You definitely can't say, oh, wait, is that 4? No, the 3's don't cancel that way. When we have the plus or minus sign in a numerator, remember, it's like they're trapped in parentheses. And so essentially, by order of operations, we have to do whatever's in the numerator or whatever's just in the denominator first before we do anything else. And so it's simply not going to work. The way that you're suggesting we cancel is not going to work. There is a way to cancel. That's what we've already seen with monomials on the last example, but it only works if we're doing proper factoring. So what does that look like here? Well, the x minus 5 stays x minus 5. the x stays x. Even the x squared stays x squared. But x squared minus 2x minus 15 can be factored, right? That is going to be the same thing as x minus 5 times x plus 3. And if you don't understand why that is, you need to go back to chapters 7 and 8 or call me and practice factoring with me. Now, I am going to pause here, right? Because I need to do my excluded values. What would cause these denominators to be equal to 0? Well, in the case of x by itself, obviously, it's just 0. So x can't be 0. That has to be excluded. For x minus 5, that would be 0 when x is 5. So we can't let that happen. X plus 3 would be 0 when x is negative 3. So we can't let that happen. So we have 3 excluded values for this problem. All right, and now we unpause, right? So let's go back in here. And do we see anything top and bottom that would cancel? And the answer is yes, right? Now that we have a whole factor, x minus 5, it's going to cancel with this x minus 5. We also have things like x squared and x, which we've already seen cancel because they're just monomials. And that's why this expression simplifies down to x over x plus 3, excluding when x is 0, when x is 5, and when x is negative 3. And we know that we're not going to cancel any further here. We're not going to do something silly like say that the x's cancel out here. So that's example 2. Take a moment, do some factoring, write out some excluded values, and simplify for me. Check your progress 2A and 2B. All right, so here are my answers. Check your progress 2A. I got 5 over x times the quantity, x plus 4. With excluded values, x cannot be 0, x cannot be negative 3, and x cannot be negative 4. And again, we do those excluded values before we cancel so that we don't accidentally miss any of them. Nothing special here that you might think would cancel, I don't believe, so that should be pretty straightforward. But definitely some things you might get confused about on Check Your Progress 2B, where I got the expression y plus 1 over y, excluding y cannot be negative 5, y cannot be 0, y cannot be 4. And again, you might be tempted to do something like cancel out the y's and say this expression is the same as 1, but it is not. In fact, that expression will never equal 1. We've got one more example. So in the same way that you can cancel monomials and polynomials in all these rational expressions and what we're simplifying and whatnot, We can also cancel units. This is the heart of what we call dimensional analysis. You've done this before. In class 6, you just called it unit converters. So take a look at something like example 3. In the 2004 Summer Olympics in Athens, Greece, Justin Gatlin of the United States won the gold medal for the 100-meter sprint. His winning time was 9.85 seconds. What was his speed in kilometers per hour? So we have some number of meters, and it is given to us as accomplished in some number of seconds. We want to do something and turn that into kilometers per hour. Well, first of all, let's start with seconds, right? How are we going to convert seconds into hours? Notice that our units of time are in the denominator in both cases. So seconds we can turn into minutes easily enough, but if it's on the bottom here, we need to cancel it by going up to our numerator. So I'm going to put seconds here, and I'm going to turn those into minutes. And then I'm going to do the same thing. Minutes, because it was in the denominator, I'm going to cancel it by putting it in the numerator and turn it into hours. From here, I just write the relationships. 60 seconds is 1 minute. 60 minutes is 1 hour. I forgot to write from the very beginning, it was 100 meters that he ran in 9.85 seconds. Finally, one more converter. We're going to take meters and turn them into kilometers. And so again, this time since meters is on top already, we need to cancel it by putting it in a denominator. So meters will go down there, kilometers will go on top, and then how many kilometers to how many meters? 1 kilometer relates to 1,000 meters, right? From here, I cancel, just as I was saying, seconds with seconds, minutes with minutes, meters with meters. And so what I end up being left with is 100 times 60 times 60. So that should be 360000. And then on bottom, 9.85 times 1 times 1 times 1,000. So that should be 9850. And of course, to actually perform that calculation, I'm just going to go to a calculator. It looks like in the book they canceled some of these zeros out. So they got, I don't know why they would do 98.5. That's a little bit weird. But you should have 36,000 divided by 985. 36,000 divided by 985. And of course, we get the same answer, 36.548. Actually, they rounded incorrectly. 36.55. 36.55 kilometers per hour. I don't know. Seems fast for a human being to me. Try and do the same thing on Check Your Progress number 3, all by yourself. All right, presuming I did not do any of my math operations incorrectly, there you have it. You should have gotten about 95 1/3 feet per second. That makes good sense to me because I happen to know 60 miles per hour is 88 feet per second. Why I know that does not matter. And so 5 miles per hour is about a 12th more speed. A 12th of 88 is about 7. So this seems to me like it's pretty good. 95 1/3 feet per second is our answer. That is lesson 11-3 on multiplying rational expressions. We can multiply and cancel monomials. We can multiply and cancel polynomials as long as we're canceling full linear factors, full parentheses, not just parts of them when we see plus and minuses. We can even cancel units, and that allows us to do what's called dimensional analysis. I hope that was helpful to you. If you have questions, be sure to comment down below or write to me, email me, text me, let me know one way or another. And I will see you around.